All right, let's get started. So today we're going to talk about substructural operation semantics, and I'll try to explain to you what that is. But it's related to substructural logic. It's just a different view of what we've been doing in the last couple of lectures. Let's think about what we did in the last lecture. Okay, by the way, the lecture notes are out, and the new homework assignment is out, and it's due this Friday. And I will try to grade it back to you by Monday so that you have some feedback before the midterm. The midterm will be a week from Wednesday, and it will be a closed book midterm. So that means that the questions will be relatively easy compared to the kind of thing that you do in the homework, because I don't expect you to remember everything, and you only have 80 minutes anyway. So I'm trying to test something different than what the homework already tests, namely whether with sufficient time and the lecture material you can figure things out. That's what the homework does, and the midterm is more like a question: have you assimilated the material well enough that you kind of, without a lot of resources, you can, answer some relatively simple questions comparatively. Okay. So what we did last time was the following. We had the linear, so we had natural deduction for linear logic, and we showed previously that it was defining the same theorems as the sequence calculus for linear logic. So they're different proof systems for linear logic, one by natural deduction, one by sequence calculus. Now, if you take natural deduction, we know by Curry-Howard interpretation of the proofs as programs, you get some kind of a linear functional programs. And the question is, how do you give an operational semantics for these? So we talked about some proof reduction, but the proof reduction themselves didn't constitute as such an operational semantics. So in order to figure out what's a possible way to assign operational semantics, we took the proof that natural deduction proofs can be translated to the sequence calculus, and we played that through on linear lambda terms to see what kind of sequence calculus proofs would come out. We assigned proof terms to these, and the proof terms are from the pi calculus, from the session type pi calculus, and that gave us an interpretation of linear lambda terms as pi calculus terms. And so the way you can execute the linear lambda terms is by doing the reduction on the image in the pi, of the translation in the pi calculus. Okay. So that gives us one way to execute things if you already know how to execute things in the pi calculus. And the biggest change there is that natural deduction operates by substitution, so in a very big step, and the sequence calculus operates by cut reduction, so in very small steps. So it's kind of a compilation, if you will. So today we're going to re-examine that. I'm going to try to present an operation semantics in a completely different way. Okay. And the idea is that we already have, okay, actually let's back up for 1 second. So when you describe an operational semantics of the language, you actually describe how some kind of abstract machine or something that wants to evaluate terms actually behaves over time, how it changes state. Okay. So really what computation is at some level is a change of state, either of some abstract machine or some real machine, but it's a change of state. So we already have techniques in linear logic to describe systems that change state. So for example, we did the blocks world example, where a change of state means picking up a block or putting down a block. And we describe these things by giving inference rules, and then later we showed how to take the inference rules and describe them as logical formulas. Okay? Namely by using linear implication and tensor and so on. So now what we want to do is we want to use our technique that we have developed for describing change of a state in linear logic, and we want to use that to describe the operational semantics of a programming language, because it also involves a change of state as a computation proceeds. Okay, so that's the basic idea. And the semantics that I want to capture in this way is the semantics that I described last time, which is the semantics of computation by interaction. Okay, so that's what I'm trying to do. Describe the computation of interaction, but describe it directly as a system for change of state, okay, expressed in linear logic in the way we did it before when we had stateful systems and we tried to capture them. Okay, so the high-level outline may look something like this. So last time we took terms m from our linear functional language, and we translated it with respect to a channel x. Okay, and then over here, maybe I should. This is probably not. Okay, let me write it over here. So m. Okay, and over here we had some kind of a translation this way. Okay, and the property that we wanted is somehow that if m has type A over here, then the translation communicates along channel X and has the same type A. Okay. So now what we have over here is some kind of a notion of reduction. And here we had some kind of a notion of computation. So that was from one process expression to some other process expression, which would still, in the end, do that. Okay, and then we could see what happens on the pre-image over here. So this has to correspond to something over on this side, some kind of value which still has type A. And we didn't actually make this part here explicit. We didn't describe exactly what the values are and how we get there. But what we did to see what happens to a term, we knew how to translate, and then that process expression by its very nature will compute and give us some kind of a result here. Okay. So now I'm going to try to describe induction in a different way. So I'm going to embed this into some kind of a stateful system. Okay, and so there's going to be a predicate eval. Okay, and the first argument of eval is going to be a term m, and the second argument is going to play the same role as the x over here. Okay. Okay. So the way I usually pronounce this is that we evaluate a term m with the destination x. You can also think of it as the same as happens here when you compute with a process. You communicate the answer, if you will, along some kind of channel x, or you communicate along a channel x. So here we do the same thing. Okay, but now this is a predicate whose meaning we describe by giving rules in linear logic. Okay, and what we want is that this computes here, and this is by a state change to some kind of return, some value v, to that same, along that same channel x, or to the same destination x that we started from. Okay, so that's kind of the picture that we're trying to go after. So if this is confusing, maybe once we start to go through some examples, it becomes more clear what we're really going after. So the way I'm going to try to read off what these rules are here is by looking at the translation and see what kind of state change it induces, and try to extract from that what kind of rules we have to have over here in order to model what happens with the computation of the process expressions that correspond to our linear term over here. Okay, so very simple example was pairs, so let's start with that. Okay. All right, so let's think about, anybody remember, actually let's do the, okay, pairs m comma n with channel x. What was the interpretation of pairs? So this is a review from last lecture. So if you don't remember, you have to go back and think about what's the type of a pair? It's A with B. Okay. What is the process expression that corresponds to A with B? It's a case. Okay. So that comes x dot case. And what are the two branches of the case? Right. They're the components. Okay. All right. And let's say if I have a first projection, pi 1 of m, and let's call this w. Okay. So intuitively, if my pair is going to be a case, then if I take a first projection of that, that's going to be sending some in left or in right. For the first projection, it would be sending an in left to that m, right? And in the proof that corresponded to taking a cut. Okay. So what was the process term corresponding to this? Okay, so we create a new channel X. Okay. Okay, so we translate M with respect to this channel X. Hopefully that will compute down to some kind of a case, right? Because that should be a pair. So this M should be evaluated to a pair. So eventually it should look like this. Okay. And then we have to send it a message, right? And the message would be, in this case, in left. So X dot in left. And once we have sent that message, where do we get the answer? We get the answer on X because this case will select the branch, but then the term underneath here will still communicate on X. So we get the answer on X, but we're supposed to deliver the answer on W. So we have to say, we have to forward X to W. Okay? So that was our translation of pairs. Okay, everybody remember this now? Okay, makes sense? Okay, so now we're trying to describe the state change that's associated with these things, okay, by using predicates and inference rules. Okay, so I'm going to start by using inference rules, and eventually I'll start writing in logical notation. Okay, so if we're trying to evaluate the pair M, actually, let's try the second part first. So if I'm trying to evaluate pi 1 of M with destination W, okay. Okay, so how do I change my state to the next state? Okay. So in order to evaluate this result, which is going to be this part over here, how do I evaluate this? Okay, so what happens when you try to take this pi calculus expression and evaluate it? So what happens is that, well, a new channel gets created in some sense, right? Because it has to be new, a private channel. We have to evaluate M, right? And then we have to have this thing somehow waiting. What does it have to wait for? It has to wait for this process here, okay, to offer to input in left or in right. So this thing here has to wait for this thing to reduce far enough that it actually becomes a case. Because it might not be a pair. It might be some function call that eventually gives you a pair. Okay? Okay, so one thing we know is we have to evaluate M, and we have to give it X. Okay? And we also have to wait somehow. Okay? And the notation here is going to be something like cont, which stands for continuation. Okay, that waits on X. And what it's supposed to do, that X dot in left, I'm just going to say pi 1 of underscore. Okay, whoops, not quite finished yet. So basically what this says is we're expecting the value of whatever was here somehow be communicated along X. And then we have to take the first projection of it. And we can't do that yet. We can't do that in this rule because this thing has to wait. And eventually we have to forward the result to W. Okay, so cont has 3 arguments. First argument along which it expects a value. The second argument which tells it what remains to be done. And the third argument is where to produce its answer on. Okay. So there's 2 components here. Okay. Now there's also this quantification over X. So what I would like to say is that X has to be new in the conclusion. Okay. So if you want to use inference rules, there is a kind of notation I devised for that, something like this, okay, which says that in this inference rule, when you apply this inference rule from here to here, okay, this thing in the state is replaced by these 2 things, the 2 conclusions, and we generate some new X. Now, we don't have to use that inference rule notation because we already talked about how to translate this into logical form. Okay. So in logical form, if you forget about the quantification at the moment, what does an inference rule with 2 conclusions look like? Right. So you would say evaluating pi 1 of m with w, then I evaluate m destination x, and in the same state I have a continuation x, like that. Okay. So, the inference rule line here becomes a linear implication. This is the antecedent of the implication, and the two conclusions are written next to each other here in the conclusion. And now the question is, how do I deal with the fact that I need a new name in the conclusion? Okay. So what I need to do in order to deal with that is I need to existentially quantify this. Okay. Okay, so if you think about when you apply the rule, what happens is you have a state here that matches this eval, and you generate this by putting it into your context. Okay, so you put exist x eval mx cont into the context, and if you have an exist x in the context, okay, what happens is that you generate a new parameter for that, a new name. So to remind you of that, let me show you the rules for it. Okay, so if you have a psi, you have a gamma, you have a delta, and you have an exist x colon tau dot a, and I'm trying to prove c. Okay, so the left rule for the existential says something like this. Okay, according to this, we know there exists an x colon tau. We don't know what it is, so we can proceed with our proof giving this a new name. Call that, let's say, n. And we record the name and the type in this context. Keep this the same. And here we have a, where the new name n substitutes for x. And we still have to prove c. And there's implicit here the side condition that this n here is new, doesn't exist before, because we added to psi what wasn't before. Okay, so that's the exist left rule. And just for completeness, the exist right looks like this. If you have gamma, you have delta, we try to prove exist x colon tau dot a. Then in psi, we have to find some term m, which has type tau. And then we have to prove that a, where m replaces x, can be proven. Okay, so that's the exist right rule. And I think I asked you to check in one of the homeworks that the left and right rule for existential actually work together, that they get some kind of local reduction property. Okay. The important thing to notice here, when you apply one of these rules by focusing on it, which will be by focusing on the left, okay, this formula will appear on the left, which means that this thing will be added to the context. If you add something positive to the context, it will be decomposed. You will choose a new name for this, and you break down the tensor into two components. So the essence of applying this rule, if eval and cont are positive, will be to replace eval pi 1 mw with eval mx and cont x pi 1 of something and w, which is exactly what this rule accomplishes here. Okay. Okay, but if you think about it operationally as a state transition, to evaluate this, we evaluate m and we put a continuation. Okay. All right, so that was part of the second rule, right? Where we took this part here and we bundled it up by saying cont of x pi 1 of something and w. Okay. So this was bundled up instead of written out. Okay. So we have to explain what this actually means related to this in some other place. Now this thing here, okay, will also be spread out over two places. So we say to evaluate the pair m comma n with destination x. Okay. So somehow we are supposed to generate this case over x. Okay. But actually, the behavior of what this case actually carries out will only be apparent once it communicates with this in left. So what we instead say, well, because nothing happens here, okay, because this thing is a prefix, So nothing will be reduced under here. That the evaluation of the pair itself is done, okay, for now. And its structure will be analyzed at some future interaction point. Okay. So a pair is actually like a value. So what we do is we return, okay, the pair m comma n to the destination where we're supposed to return it along. Okay. And so what happens is if you do pi1 of a pair, evaluating this or reducing this will eventually return the pair to this place here where it waits to interact with that. So this eventually will become, after some transition, a return of some kind of pair m1, m2 to x. Okay? So now we have the two pieces. We have a return of a pair to x, and we have a continuation that waits for something on x. Now the two actually have to interact. Okay, so let me write that up here. So if we have a return of a pair m n to x, and I have a continuation that waits on x, wants to take the first projection of what it gets and passes the result to w, then we can make a transition. Okay, so what should we make a transition to? Right. So we need to now evaluate m. And we need to give m a destination when we evaluate something. So this evaluate m comes because we're sending the in left to this. That will select the first component, which means that we're evaluating m with that destination x. Right? So we evaluate m with destination x. Is that everything we have to do? That's no, because we haven't accounted for the second part. Okay? So in the second part, what do we have to say? Well, we have to listen on x and forward the result to w. Right? So we would say, and we have a continuation that waits on x, does nothing, and forwards the result to w. Okay, so that's the second part of this. So the first part is to extract m from the pair, which is the same as extracting the first part of the case here. And the second thing is to actually sort of tie x and w together, which is like a continuation, except we don't have to do anything in between. We just tie them together. Okay. Does that make sense? Yeah?
Question about the use of exists x over there.
Yeah.
So if I said exists x dot some term in the syntax and then said exists y, are we assuming that x not equal to 1? Is the vernacular strong enough to assume that?
Okay. So what happens is there's an exists y here at the beginning of a. Okay. That will create a new parameter into the context, which would be some other parameter, say small m. Okay. Which is different from the one that we have before. We make no assumption about the parameters at all, except for its type.
Except in the operational semantic when we said new x,
Yeah.
we were making I'm feeling we were making a slightly stronger assumption there that x is fresh, whereas here, when time checking, we do assume we do add a new variable in the context, but when I normally think of the existential modifier in propositional logic, it's something bigger.
Right. So the way we interpret these things here, this has to be fresh because if it were already declared in psi, you would have to pick a different name. So it is fresh in that sense. Okay. So it's a little bit of an odd interpretation of the existential quantifier. So if you want to check the details to see that it really works out, you would have to apply focusing to these rules to see that it generates the right derived rule. Okay. But it actually will. By the way, I should say here that in each of these, there are some free variables, okay, which are implicitly quantified over the whole rule. So there's an implicit quantifier for all m and for all n and for all x and for all w. for example. And here that would be for all m and for all w. That's it, right? Because x is quantified here, so we don't quantify it on the outside. Okay. Okay, does that make sense? Okay. Yeah, I think there's more to say in answer to your question, but I think it would lead me too far afield if I try to go into more details. So just think, if you just look about this as this rule, you see that we add something here to the context, which has to be different from anything else that was declared before. Okay. All right, so that's the pairs. Okay. So now we have our rules for pairs, and now we want to reconstruct the operation semantics for other things in the language. So let's try to do functions. Okay. And we try to follow exactly the same roadmap. Okay. Yeah?
For completeness, don't we want the continuation on the identity?
Hmm?
So right now we don't have the continuation on the identity. So at a return, so cont x to y with the return value.
Okay, so we didn't talk about that. So we should talk about that. So if you have a return of value v to x, and we have a continuation that waits on x, and when it puts its result into w, what will we do? Yeah. Okay. If we're not sure that in this bidirectional plugging together, we're actually getting the right directionality, always, that we always return something to the first part, we never return something to w, we would add a second rule, right? So we could say if some v is returned to w and we have a continuation x underscore w, then we return the value v to x. Okay. So we'll have to examine if we would need such a rule. It's not obvious that you don't need that, right? Because the arrow that ties together x and w goes in both directions. So let's put a question mark on that. Okay. Okay. Now remember that all these things are linear. Okay. So for example, if we're supposed to evaluate a pair, this is a state transition. We go from eval to return, and the eval is consumed in that, so it can't fire again. Okay. And similarly, if we evaluate this, we go to here, we replace that eval by a new name, and this eval and this cont. Okay. So these all rules describe change of state of some kind of abstract machine. And the property that we want in the end is something like this. That if you start with eval, so m with w, then as a state transition, we make a bunch of transitions. So let me write it like this. And eventually, we return a value v to w. Okay. And there could be other things in here. And they're not affected. Okay. And that's because whenever you have state transitions, they don't depend on the absence of anything. You have this kind of a frame property that you can add something here and you end up with the same thing over here. Okay, that's just the property of linear logic, that we don't have any rules that can test for the absence of things, so the same rules will still fire. Okay, yeah?
The reason that we don't need the top rule is the reason is that this will form kind of a tree-like structure, and there's no looping.
Right. So we will try to arrange that whenever we return something, it can only be at the beginning of a continuation, and it's hard to say until we have done all the rules. But right now, it looks like it will be some kind of a tree-like structure, right? That evaluation of one thing spawns evaluation of other things. But you see, we evaluate with x, and x is at the beginning here. We don't evaluate something directly with W as a continuation. So I think your intuition is right, but we have to look at it when we're done. Okay? Okay, any more comments or questions here? Okay, so let's look at functions. So now we have to remember how these things are compiled. So lambda y dot m with respect to x. How do we compile a function, which is like linear implication? Yep, so we listen on x for y. And once we get the y, we have to execute m. And m can depend on y. So let me put the possible dependency here. And what is the channel that it communicates on? To its value? On x. Okay. So we receive the argument on x, but we also communicate our result on x, which is a linear channel, so that's perfectly okay. So here, before you start this, x has type A or B. After you do the input, x has type B. Because as part of the input of our session, now our type is to be B. Okay? All right, so m applied to n obviously has to be more complicated. So we'll translate that with respect to w. Okay, how does application work out? Anybody remember? It's just a cut, right? Because we need to get the implication on the other side. So that means there's going to be a new channel, and there's going to be two things that we have to do underneath. So the first part of the cut is which? M is going to be of type A or B. So we take m and we translate it with respect to x. So on the other side now is going to be x of type A or B on the left-hand side. So we can apply implication left rule to that. Implication left is the same as sending a message to a process that's waiting on the input. Okay. So we have to send on x. Okay, what do we send on x? A new y. New y. We send that on x. Okay, once we have sent that, okay, what happens next? We have to translate n. Okay. So where does n want to communicate its value? Y. Because that's the channel in which, see, m is supposed to communicate after it gets the argument y. Okay. We're not quite done yet. What else do we need to do? Right. We need to get the result of the whole application to be on W. So we have something here that we have to communicate on W. And where do we get the value from? It's going to be x. Where does x come from at this point?
Well, it's the same channel with the implications change type.
Right. It's that value of the implication. We have sent along this channel the argument y of type A, which is tied to the result of n. And then x changes type and actually now communicates its answer to here, which we then forward to W. Okay? Okay, let's look at how variables are translated. Yep.
So, is there a principal reason why we have to use a different channel X and not W?
If you put W here, you mean?
Well, W was already waiting for something, right? So we can't send it the Y if we put it there.
Right. W here is going to be of type B, right? But you're going to have to send M is going to be something of type A arrow B. So just by typing reason, it can't really work out. Okay. But something is already sort of waiting on W as the output of this whole thing. So if we name this W, there would be a confusion of linearity, and two things want to communicate at the same time. So when you send to W here, it could either be received by M, or it could be received by whatever is waiting for the result of the application. So, okay, so neither types nor linearity work out. Okay, we have to translate variables. So if we translate X, W, okay, what's the translation of a variable? Yeah. Forward X to W. Okay. All right. Now we just have to see if we can translate this into our formalism over there. Okay. Basically translate these rules into state change rules in linear logic. Okay. Okay. So let's start with the one in the middle here. Okay. So to evaluate M applied to N with the destination W. Okay. Okay. So what do we have to do next when we try to evaluate M applied to N? So let's look at over here. So if we have to create a new X, right? New destination. So the first thing will be to create a new X. Okay, so then what's this part correspond to? We have to evaluate M, right? And that should proceed right away. So eval M with destination X. Okay. And now we have to worry about all of this. Okay. Now that can't actually compute yet. That has to wait until M there produces a function, right? And that's because this is an output prefix, and the output prefix in the synchronous pi calculus can't really fire yet until this is offering to do an input. But it doesn't necessarily offer an input. It might have to compute before it does that. Okay. So this thing will have to wait. So by our previous idea, this should turn into a continuation, right, that waits on, is it X? So we have a continuation that waits on X. We have to remember what we have to do. So we want whatever we get on X and apply it to N. And then we have to pass on the result of that to W. Okay? Does that make sense? Okay. Now we have to translate the first line here. So let's put that over here. To evaluate a lambda expression, oops, sorry, with destination X. Okay, what do we do? Well, we can't really quite do anything. And in fact, in almost any functional language, a lambda expression is a value by itself. Okay, so we just return. In the interpretation of lambda x, the input y along x will happen when it interacts with the continuation. So we return lambda y dot m to x. Okay, so the last rule here is if you have a return of a lambda y dot m to x, and we have this kind of continuation, okay, so now is the place where this part here is going to be plugged in here, is going to interact with this continuation. So what do we get out of that interaction? So this new y means we have to create a new y, right? So we have to create a y. Okay, what do we have to evaluate now? So from this part here, what do we have to evaluate? Yeah, we need a substitution.
Well, there's really two things
Yeah.
that we have in the evaluation
Okay.
possibilities. So M and M
Okay.
are both possibilities for evaluation. So I don't know, I can't see we have a dependency on which one is first.
Okay. No. So what happens is that after this interaction in the pi calculus, this will be at the top level, and this will be at the top level, and this will be at the top level. So they all can compute. So we get 3 eval. Well, we should get 2 evals and a continuation, right? So we should evaluate M. Evaluate M with some destination. We should evaluate N with some destination. And we should have a continuation that waits on X, does nothing, and forwards to W, right? Okay, so now we need to create substitution somewhere. So maybe it would have been better if I'd called this Y prime so there can't be any confusion, okay, between names. Okay, so now what is the M? So this Y prime is actually the thing that I called Y over here. So let me call this Y prime, right? Because that is the thing that is new here once we uncover this part. So this is the thing which gets created. It gets Y prime. So what do we evaluate? Do we evaluate M? Well, that's the stuff at the top there. We actually substitute because we actually do the communication. So Y prime is substituted for Y in M. Okay? So what we evaluate here is not exactly that, but it's going to be M, where we substitute Y prime for Y. And what's the destination of M? X, right? What about N? Does that get evaluated as is? Well, N gets supposed to be evaluated with respect to Y prime, but Y prime is the thing that we introduced. So N gets evaluated as itself. And what's its destination? Y prime. Okay. And the continuation still goes from X to W. Okay? So we're just writing out what the process over there would do once the first part is known, and the second part is a continuation that's still waiting. Okay. So you see that there's a parallel semantics here is that we take the body of the lambda expression, okay, and we evaluate that in parallel with the argument, and something that waits for the final result, okay, and forwards that to W. Okay. Okay, any remarks on this? Does it make sense to everybody? Okay. Third rule, we still have to worry about what happens when we evaluate X, right? So if during the evaluation of a term, we come to one of these X's. So, okay, I'll put it here. When you evaluate X with the destination W, what happens? Just read it off over there, right? What should happen? Yeah. You have a continuation, X, do nothing, and pass the result on to W. Okay? Okay, does that make sense? Okay, everybody on board? So maybe we should do a little example and get some intuition about how this kind of semantics works. Okay, so I want to evaluate okay, so let me see what kind of example I want. I want to take let's see. Lambda x. I'm going to take the first component of the pair x comma x, and apply that to some kind of value v. Okay. So in particular, actually, sorry, and the whole thing works with the w. And so to start with, I have a destination w. So I write the destinations that I have in the left-hand side. So at the beginning of the computation, my whole state looks like this. Okay? What should we get at the end here? Can we predict what the outcome should be? Down here, eventually, hopefully. Should be v, but what does it mean to return v? Okay, return v to the initial w, and w better still be one of the destinations that we have. So if we did things right, and this is our initial state, so that would be delta 0, we would be able to get to some delta n down here if we do the correct computation. Okay, so what happens when we're trying to compute eval of this application? Okay, so we have to look over there what happens for an application. So we have to replace this by using this rule here, right? So I'm actually writing things downward, even though in a focusing system it would really be going upwards, because we start with delta 0. We're trying to prove something we don't care about. We focus on this rule, and then we would get delta 1 here, and we try to prove something we don't care about. So the focusing system builds the derivation upwards, but I'm going to write it downwards because it's easier to think about it this way as a change of state. Okay, so what do I replace this eval by? What's the first part? Okay, we create an x. Actually, let me call this y. Okay, so the first part would be evaluate lambda y, first projection of the pair y. Y. What's the destination of this? X. Okay, what else would be in the context? The continuation that waits on x. What does it want to do with the result? Apply it to v and put the result to w, right? Okay, so the state change in the computation is from this state, which corresponds to sort of saying, please evaluate me to these two things in the state. Okay, now how does this compute here? The eval lambda y pi 1 of y. Yep, so we just return lambda y pi 1 of pair y to x. And the continuations should stay the same. By the way, I wrote this down without talking about the typing, but hopefully people see that this is type correct. Okay, so this will take an argument of the type of v. Then there's a pair. It looks like it's not linear, but why is it okay? Because it's a width pair, so it means that each variable in the scope of this has to occur linearly on both sides. So we just use it here, and then we take the first projection of it. Okay. All right, so now we have a return together with a continue. So if we did everything right, then another rule should kick in, which is this one here. So what does it compute to? Do we get any new parameters in the context? Okay, so we have w, x, y prime. Okay, what's the first part there? Eval. What do we evaluate here? Right, so it's pi 1 of y prime, y prime. What's the destination of this evaluation? Is it still x? Okay. The continuation is going away, but we also have to evaluate the argument, which is a v. And what's the destination for the argument? Y prime. And one more, right? Continuation that takes x and forwards it to w, right? Did I do that right? Okay, so now this thing could fire or this thing could fire. In fact, the evaluation of this can be interleaved with the evaluation of that. Okay, because in these kind of concurrent systems, A state change is described as a possible change. So this could change state or this could change state. Okay, so this could actually, this is the value already. So if you evaluate a value, what happens? We just return. So this just becomes return v to y prime. The continuation doesn't change, I assume. And what does this evaluation turn into? Hopefully the rule for first projection is still up there. Okay, so we evaluate the pair y prime comma y prime with what destination? Okay, z. So we add wx y prime z. Okay, we have that. What else do we need? Continuation, listening on z. Take the first projection of its argument and put the result where? X, this one here, and together with the return. Okay. Okay, so what happens at this point? Right, because this is a pair is a value, right? This turns into a return. So we have wx y prime z. We return the pair y prime along z. And the rest here doesn't change. In fact, the whole rest has to wait, right? This cannot continue because we have nothing along x being returned along x. This can't return because nobody's listening on y. This continuation can't start because there's no value being returned to z. So everything is blocked except the first part. Okay, presumably this return unblocks something now, right? So we have this return and this can't. Okay, so this all stays the same. Well, maybe not. So what happens? So this return and that can't. So now we have to look at the rule for that. Is this one here? This one, right? Okay, no new name. And so the first thing is an evaluation of y prime with what destination? Z. What else did we get into the context here? A continuation on z forward whatever to, what's w? X. And we still have the return v to y prime and the continuation on x to w. Okay, so what happens now? Right, now we're evaluating a variable. Okay, does that create any new names? No, so the names stay the same. And here we just, what do we do here? Is that a continuation that ties y prime to z? Is that right? Okay. And we have the continuation which ties z to x. We have the return of v to y prime. And we have the continuation on x to w. Okay, so that's our current state. So what happens now? So we have a return on y prime, and finally we have a continuation waiting for it on the other end. Okay, so that means that the body of the lambda expression for this return came from. Finally, we access the variable y prime. Okay, and so this actually communicates with that. And what does that correspond to? That's got to be this rule here, right? Okay, so now these two actually, what becomes of that is a return of v to z, right? So v returns to y prime, which forwards to z. And the continuation z to x stays. And the continuation of x to w stays. Okay, so what happens next? Okay, so this gets forwarded to x. And what happens after that? Get forwarded to there. And so after 2 steps, we just have return v to w, right? Which is what we wanted, right? I just wrote it 2 lines too high. Okay. Okay, so we have a single thing in the state. We do a whole lot of computation. At the end, we have a single thing in the state. Now, we have a bunch of destinations here, a bunch of names that have been introduced, which stick around. So at this point, we have w, x, y prime, and z. Okay. And only w really is used anymore. Okay, so if you could garbage collect these things, only w would actually remain. Okay. So these names there, they show up in the psi context that we talked about before because they're variables, they're unrestricted variables. But this is the only thing in delta. Okay. All right, everybody see how this works? Okay, so let's try to work through one more construct, okay? Because I want to see how replication works because of bang, right? Are we okay with this example? Okay. Okay. And I'm not going to prove this because it's very tedious to even formulate this. But you can see that the operational reading of these rules really corresponds to the reductions on the pi calculus onto the translation. Right? I mean, because we're the motivating factor, as you can see that if you take a step in the pi calculus, you take a corresponding step here and vice versa. So we arrange for a bijection so that this substructural operation semantics here captures exactly the previous semantics that we had. Now we can do some optimizations on this. If you don't care about the precise correspondence. So for example, here, okay, what you could do is instead of evaluate m with destination x and then forward x to w, you can kind of quote unquote optimize this and evaluate m with destination w directly. Okay, so no reason to compute it with destination x first and then forward it to w. Evaluate it with destination w in the first place. But I'm not completely sure about what rules of optimization one can apply and what cannot apply. I'm pretty sure that this is safe because we sort of derived it step by step from our pi calculus semantics. So, okay. All right, so let's do bang. Okay. So now we have to really strain ourselves to remember what happened with bang. Okay. So we had the elimination form was let bang u equals m in n with respect to w. We had the bang m form with respect to x, and we had translation of variables u with respect to w, or let me use, yeah, okay, w, fine, okay. All right. Anybody want to take a shot at any of these? We kind of have to reconstruct the proof that this kind of thing really works. Maybe with bang m we can try to take a shot at this. So what's an unrestricted m? Right, we have a persistent process that listens on x, inputs a y, and what does it do when it gets a channel y? Right, it spawns a copy of m with y. Okay, so remember what the persistent m, the replicating m, or the bang m does, because it can be used many times. It accepts a channel as an input and it evaluates essentially m with this new channel that was given. And because this is replicating input, we can give it as many channels as we need the variable x. Okay. So if we need the variable x 3 times, we send it a channel 3 times. If we don't use it at all, we never send it anything. And it's okay because this replicating input doesn't have to be consumed. Okay, it's not linear. Okay, so if you actually use a variable u, what does it correspond to?
Copy rule?
Yep, so it's like use of the copy rule. So what we have to do is we have to create a new channel. Y. We have to send y to u, okay, and right, and forward y to w, okay. Now with some abbreviation magic, we could just send w to u, okay, but generally speaking, before you get fancy with abbreviations, it's good to just do the straightforward thing, because sometimes these things work out well and sometimes they don't. Okay. So here, whenever we reference a variable, presumably it's waiting on a replicating input. So we send it a new name, and that new name stands for the value w. Okay? All right, so now this one is the last one here. Okay? Let bang of u m equals, bang u equals m and n. So what do we do first here? Cut, excellent. So we create a new x. What's the first part of the cut? That's going to be m. We're going to translate this with destination x. So that's going to have type bang a, because we do a bang elimination, right? And so x is now type bang a in the environment in the rest of this, right? And this produces something of type bang a. So now we have x colon bang a in the environment. What do we do with that? Yeah, okay, bang left, exactly. Anybody remember what the term assignment is for bang left? Yeah? Right, it's x for u in the translation of n. And how do we translate n? With respect to w. Okay, and it makes sense. N contains u. So if I want to make that explicit, I would write u here. And so, but then we substitute x because x is the one that we cut here. Okay. All right, good. So now we just have to translate this into our substructural operational semantics rules. Okay. Okay. So what happens with, I don't know, bang m? Oops, not equals. Goes to? Yeah?
Well, we're not supposed to evaluate anything anymore, so it's some kind of return.
Yep. So it's a return, okay, of bang m to x, right? Because this thing can't really do anything. So this interpretation of what this actually does will happen in a different place. At this point, we just say, well, we can't do anything. Okay. And presumably, from this rule, somebody will be waiting to communicate with it. Okay. Okay, so now that rule, to evaluate a let bang u equals m in n with destination w. Okay. What do we do first thing on the right-hand side? Yep, we have to create a new name, exists x. What's this correspond to? It's an eval of m with destination x. Okay, and what's this correspond to? Well, it can't really do anything, right, until we get something from here. So it will have to be suspended, so it will be a continuation. What is it waiting on? Not quite. U isn't even free in this because this binds you. It has to wait on x, right, because we evaluate m with destination x. What is it supposed to do when it gets its value? well, say let bang u equals blank in n. And where it's supposed to put its answer? W. Okay? So all of this stuff here is just going to be wrapped up in this continuation, right? The only free variable it has is x. And of course, w at which it puts the answer. Okay? So the interesting part is going to happen when this eval returns something. Okay? So it interacts with this continuation. So if we have a return of bang m to x, and we have a continuation which waits on x, wants to do a let bang u equals underscore in n, and eventually forwards its result to w. Okay, so now we have to put here on the right-hand side what happens is when this thing interacts with that. Okay. So what happens at that interaction? Okay, so let's write it out here because this is tricky. So we have new x, and we have bang x, y dot translation of m with respect to y, and parallel with x for u in the translation of n, which depends on u, and this translation is along w. Okay. So anybody remember what happens at that interaction? Right. So what happens is this is a difference between, so this corresponds to a cut on the formula bang A, where the label of the channel is x, right? Because this is of type bang A on x, and this expects bang A, x colon bang A on the left. And that turns into a cut bang, so this turns into a cut bang on the formula A, except now that we're cutting out the formula u. So this reduces to nu u, bang u y, my. In parallel with this prefix disappears, and we have n, which depends on u, w. Okay, so that's what has to happen here, this kind of reduction. So how do we translate that? So we need a new u. Okay, so we do exist u. Okay. Okay, we need this part. Okay, what is that part? Tricky. Okay, so we don't know what to do with that part. What do we do with this part? We should just evaluate n with destination w, right? Unless I made a mistake. Yeah, it's the same w here. So we evaluate the body of the let, okay, with the destination w in which it's supposed to return something. Okay. So the tricky thing is, what do we do with this? It should be a continuation, waiting on well, what's this thing waiting on? It waits on you, right? And who will send a message to you? N, but when will a message being sent to n? Via n? When it encounters you, look. Okay. If in n we come across you, then we send a message to you. Make sense? Okay. So we could say this is a continuation. It's a little bit odd because we don't have any place for something to pass it into. So we expect something on U, but we have no place to send it onto because the place we're supposed to send our result will be sent to us first, right? Okay. So another way to say that even though this accepts an input, I'm going to view this thing still as a value. So I'm going to redo a return of M to U, okay, except that this has to be persistent. Okay? This is not the only way. So the way that you propose make this a continuation is another, except that it doesn't have a destination to send something to. So let's see if we can make this work out, because we have to say what happens when you evaluate U. If you evaluate U with destination W, okay, what do we go to if we take this point of view here? So when can we perform this output? Yeah? And? Okay. Exists Y. Okay. Well, not on that channel. We have to wait until U is willing to communicate, right? So I would say we wait on U, and what do we want to perform when we see that? Forward the result to W. Okay.
Why did we need to do?
Hmm?
So why did we need to do this one?
Good question. So maybe the way we did the bound output before is that we didn't actually introduce it until the communication took place. So maybe we should wait with introducing Y. Okay. So let's see what happens. Okay. So now this kind of return interacts with this kind of continuation. Let's see if that works out. So what would happen is, let me put it here. So if we have a persistent return of M to U, and we have a continuation that's waiting on U and forward the result to W, okay. What should we do now? Now we need to do this thing, right? We create a Y, exists Y, and what do we need to do? We evaluate M with destination Y, evaluate a copy of M with Y, okay, and the second part is forward Y to W. Oh, sorry. Cont. Okay, so that would be one way to do it. And I think there's another way to do it where instead of having persistent return you have a persistent continuation, which waits on you, okay, but somehow it doesn't have a destination to put its result onto. Okay, so maybe this is the better thing to do. So the persistence of this thing here, the fact that this is persistent is captured by the fact that this return of M to U is persistent. So when you come to U multiple times, then this will fire multiple times. And every time it fires, it interacts with this return, which is persistent and continues to be there, and spawns a new evaluation of M, and then forwards the answer to W. Okay. Okay, so this is the trickiest part of the whole translation. The other things like tensor and sums and so on, disjunction, all work out easier. Okay. So it's a little bit odd because the flow of information here is a little bit, it's weird because in the let bang, when you have a variable u that's bound on the outside, you have to send it a channel. So somehow that has to be accounted for. Okay. So this is one way of doing it. Okay. But somewhere we need a bang in this semantics. Okay, that's clear. Because something needs to be persistent because we have a persistent input here. Okay. Okay. So I think that with this particular way I wrote it, it still corresponds exactly. The steps of evaluation there still correspond to transitions, state transitions here. And what happens when the bang return becomes part of your context here, what happens? So this is a question about the focusing system, right? Because the left rule for bang is invertible. So you introduce a new u, you break down the tensor into this, and then because this is a bang in front of it, because it's invertible on the left, it's moved into the persistent context. So this thing, return mu, will be in the persistent context, which means that it can participate in this interaction, okay, as often as it needs to. That is, as often as the variable u is being referenced. So then what we see is that it doesn't actually look like that in the full language, we don't just go from delta and we take some number of steps and we get to some delta prime. But really what it looks like, we have some gamma and some delta. It takes a number of steps and we get some gamma prime and some delta prime. Okay. The difference is that the gamma prime is always an extension of gamma, because as we move forward, we add new things to the context. We only got more things into it, while the delta actually changes to delta prime. And how does psi behave? So what do we get over here? Right, we get some kind of a psi prime, and it's strictly large, and what does it contain? It contains all the destinations, all the names that we created with these existential quantifiers here, right? Because they end up as new parameters in here. So psi prime is always a superset of psi, just like gamma prime is a superset of gamma, while delta changes to delta prime. Okay. So this is quite a flexible way to specify the operation semantics of programming languages. So you can do, basically any kind of thing we've tried to do in terms of call by name, call by value, continuations. Ian here has tried shift reset in probably different versions, store, exceptions, and so on. You can do all this and describe it in this way. And we always have these three predicates, eval, return, and continuation, to describe three different things that actually happen. So the intuition is that when you evaluate something, it can always make a transition. It doesn't have to depend on anything. You can always change by taking eval to something else. A return is something that offers a value along some kind of to some destination and hopes that somebody else is waiting on this channel to receive a result. And a continuation usually has one input along with it's waiting for something like a return. So a return matches up with a continuation. Then something else to do once it gets the value, and then some final destination on which to put its value when it's done. Now there are some concurrent languages where you can't quite do in this simply way, because if you have like a synchronization primitive, like a join where you have to wait for two things, then you might need to have two names here as input before you can proceed with something else. But the general scheme is still very similar in all these kind of semantic descriptions. Okay, so just to summarize, what we did today was to sort of elevate ourselves one level. We now think about the things that we're manipulating as being terms in some language that as a compute change state, and we want to describe this change of state using the technology of linear logic. Okay. Now I call it substructural logic because it turns out that depending on what you're trying to do, linear logic may not be the exact right tool. Okay. So sometimes you want something weaker even, okay, And sometimes you want something stronger than just linearity. So here we use linearity, but we had some persistent assumptions. Okay. Sometimes it's convenient to have affine logic where assumptions don't have to be used. They can be left over at the end and so on. But here, since we're describing the semantics of linear functional programming, it turns out that linear logic here in the meta language is a very good match. Okay. So that kind of closes the circle, because at the beginning of the semester we started and we said to describe stateful systems we can use kind of either inference rules, and then we turn them into logical formulas to describe how a system may change state. And then we investigated some kind of internal reductions in the linear logic that would derive from that, where we had left rule meeting right rules giving rise to computation. In natural deduction, it was introduction followed by eliminations, which gave rise to substitutions. And now we're going back to the very beginning. We use a system that we used to describe trait transition to describe in a different way how computation actually behaves by looking at the language as now kind of an object. So we're putting ourselves sort of one level above the thing we're trying to describe. And it turns out that this is a very general mechanism to describe the operational semantics of programming languages. Are there questions on this? All right, well, I'm not exactly sure where I'm going to go next, but I'll figure it out by Wednesday.